Then let's look at another example, the RC filter. Let's remind ourselves what is a RC filter. Here is something called the low-pass filter. We have a resistor here, we have a capacitor here. The input is here, the output is here, right? How do you find the output in terms of input? We'll talk about that later. But let's try to model the noise. Okay, here I only care about the noise. The noise, where does it come from? It only comes from the resistor. In our class, we assume the capacitor and inductor are ideal. Now, if not, what can we do? We just add a parallel or series resistor to it, then it will have a noise. Here, we assume it's ideal, no parallel, no series resistor. And because of this is the equivalent circuit. Now I make this R ideal, and then I say I have an extra noise source, which is 4 kTR1. And actually, not to confuse everyone, here we actually don't have this, right? This is not R1, this is R only because I call this R, right? So this is 4 kTR. Okay, so this is 4 kTR, and then our question is, how much noise do you get from here? Well, this is very similar to what we did earlier, isn't that? Look at this. You're asking how much noise I get from here with this noise source. The only difference is that I have R2 here, but here I have the capacitor. Not a problem. We just work in the frequency domain. So we just write down the impedance. The output power spectral density, right, or the power equals to the input power times the impedance of the capacitor divided by impedance of the capacitor plus the impedance of the resistor. Impedance of capacitor is 1 over SC, right? 1 over SC. Of course, impedance of resistor is just R, right? Then you times SC, you get 1 over 1 plus SRC or SCR. The input noise, the noise source, of course, is 4 kTR. We know this very well, thermal noise, right? Then how about the absolute value of 1 plus SRC? Now, if you forgot, S is just J omega. J is square root minus 1. So this is a pure imaginary number. And if you remember, A plus JB square, their magnitude square, is just equal to A square plus B square. So this is equal to 1 square plus omega square R square C square, because S is just J omega. Okay, please pause and try to track yourself, see if you can repeat what I'm doing here. So again, what is this? This is the power spectral density. It's talking about the noise power as a function of frequency. And now you see as a function of frequency because omega is 2 pi f. You see that when omega is 0, then we have the largest value because this term is 0. But when the frequency increases, eventually this one will dominate, and then also the whole term will decrease because I keep increasing omega. So if you plot it, you will get this shape, right? Remember, originally this one is white noise, so it's straight forever. But now because of this filter, it has higher value at low frequency and lower value at high frequency. Right? And what we're talking about is this point, of course, right? So this is the output noise power, PSD or SXF, whatever you want to call it. Then what is the FH noise power? Let's go back to here. This is the FH noise power. It is the integration of the power spectral density, the integration of Vn squared. Okay? So the FH noise power is the integration of this area. So you just do an integration over frequency. We did not show the step, but eventually you will get 2 pi kt divided by c. Right? In this class, we are not going to test your integration skills, so no worry about that. Then what does it show? That's very important. It is independent of R. Your FH noise power has nothing to do with R. Why is that? Because when the R increase, okay, I do have more source noise from the source, but at the same time, 1 over RC reduce. This term you will start reducing much earlier. You can even say that maybe it is something like this. And this will have the same area when you do the integration. And that's why it is independent of R. Okay? So how can I further reduce the noise? I can increase the capacitor, right? Or I can also I can also reduce the temperature, right? Because if I reduce temperature, then I have less thermal noise. Makes sense, right? Increase capacitor, I can push this more to the left without changing the peak, the top, right? The top is 4 kTr, right? If I reduce capacitor, you won't change this one. So as a result, you have a smaller area. Okay, so this is I think it's a very good exercise, right? To understand how to calculate the noise, to understand some of the critical features. So please make sure that you know how to do it.